Hello everyone. Time to take a flight through the universe. Welcome to Wausau, Wisconsin, our first stop, looking up at a beautiful blue sky. What we're going to do next is blast off into space. Let's get high above Wausau and zoom out into orbit as we begin our journey. Now on this journey, I would like us to always think about space and distance in terms of transmission. If we were to call home, or if they were to call us on this journey, how long would it take that transmission to get to us? So what I'd like to do next now is turn on our distance from our object. So I'm going to go ahead and turn on our distance from the Earth. Let me make that a little bit bigger for you guys to see. There we go. So we're currently about 25,000 kilometers from the Earth. And we're going to be flying back away from the Earth here, but I always want us to keep in mind that distance lag time in communication. So let's fly backwards now. And our next stop, you probably know our nearest body around the Earth, is the Moon. And it's right there. And so the Moon's orbit is, less than 600,000 kilometers. And if we were to call the Moon, it would take 1.3 seconds one-way travel and then 1.3 seconds back to the Earth. Not a huge deal, but certainly would make for a very awkward conversation. All right, let's travel back even farther now, out to the realm of the planets. And when we reach this area, we measure distance to planets in what are called astronomical units. One astronomical unit is the distance from Sun to the Earth, shown in blue. And it's like a measuring stick, and so we can measure the distance to Jupiter, or Mercury, or Saturn in terms of astronomical units, or AUs. So here are the other planets, and out in this area, we're looking at Mars being about a 12-minute delay, out to Pluto, which is about a 5-hour delay. And we're traveling through the asteroid belt right now. You can see there's a lot of them. And we're going to travel out to our farthest machines that have ever left the solar system. And maybe you already know what those are. They were launched in the the late 1960s. They've been traveling through space at 14,000 miles per hour since the 60s. And you can see their orbits in the green and yellow right there. Those straight lines in green and yellow. They are, of course, the Voyager 1 and 2 spacecraft. And Voyager 1 and 2 has been traveling through space at 14,000 miles per hour since the 60s. And they've only reached this far. But how far is this in terms of our radio communication? It takes about 16 to 19 hours for Voyager to transmit back to Earth. Yes, they are still transmitting. And so even though they've been traveling through space for 40 years or 50 years now, they can still send their transmissions back to us in about a day. So we're only one day from a communication lag. Let's travel back even farther. And let's get out to the edge of our solar system, what is called the Oort cloud, and that is the edge of our solar system right here, about 5,000 astronomical units, which is about 2 light years. So as we're out here, we're actually starting to see a 2-year communication lag. So if you sent a signal out into space today, you would see about a 2-year communication lag. I'd like to turn on our friends, the constellations, at this point. And you can see that they're all there are familiar. There's Leo and Gemini, and Orion is rising over to your right. And we've got all the familiar, friendly constellations. There's Big Dipper over to your left. But what I'd like to do now is, as we travel backwards, watch what happens to our constellations. And I'm going to turn on the exoplanets. All the green dots are planets discovered around other stars. So as we travel out, let's just watch the constellations as we fly backwards in time and space. Oh, you can see all the planets from the Kepler mission over there. Ah, we've reached a stopping point. That blue sphere that you guys see, that is the edge of humans' radiosphere. So that blue sphere that you're seeing right there, that is the farthest that humans have transmitted radio into space. And so outside of this bubble, there is no more communication from humans at all. It's radio silent. So what else is out here now that we're beyond the realm of our radio transmissions? Well, let's travel back here and see where we live. You can see all the exoplanets there. And you can see at this point, the constellations of our night sky, they're really very close by. And so we've reached the limit of human seeing. That all the stars you're going to see from this point forward are from telescopes only, from large telescopes. And we start to get out to a point where we see where we live. And this, of course, is our Milky Way galaxy. The Milky Way galaxy is 100,000 light years from edge to edge. So if we were to travel from one edge to the other, there would be a 100,000 year lag in communication. 100,000 year lag. So when you look at this, you see there's billions and billions of stars and planets. You know, what are the odds that we're alone in the universe? Well, are there other galaxies out there? Well, you might be saying, well, yes, there are. But where are those galaxies? So let's fly out and see if there are other galaxies out here. The nearest galaxies to us are called the local group, and I'm going to increase their brightness here so you can really see them very, very easily. And as we fly past them, you might notice that they're not just, stars that you're looking at. These are actual galaxies like our Milky Way. Each one is hundreds of billions of stars. And I want to travel here to about 65 million light years, because that's a very special place for many of us. If the dinosaurs had radio transmitters back in the Jurassic era, and they sent a signal out into space, this is about how far that signal would have gotten, out into the realm of galaxies. Well, of course, they didn't have radio transmitters, but it's kind of cool to think about, Stegosaurus, the greatest dinosaur of all time, having a radio transmitter to send something out into space. Well, what I'm going to do next is I'm going to back us up here so we can see if there are indeed other galaxies and how far they go. So this is the local group. Now, when we start looking out farther and farther, it's harder to see if they're spiral galaxies or elliptical galaxies. And so what we've got here are just dots on this next data set. And so let me show you guys all of the known galaxies in the universe. There they are. The yellow dots are the 2DF study and the Sloan Digital Sky Survey study. All these are galaxies. You can just see how many galaxies there are out there. And we're not at the center of the universe, we are just at the center of our map, because we map the universe conveniently placing ourselves at the center. Now you might be looking at this saying, okay, why is there big triangles of data missing? Why does it seem almost like the data is in sandwiches? If we get down here, you can see it's almost like in layers. Well, that's because this is the only place we've looked so far. These surveys cost money and cost time, And so when they look to the sky, they can only get swaths of the sky in one study. And this is so far what we've got. Now, you might be wondering, what is that background picture? Let me turn off some things here to clean some stuff up. This is called the microwave background radiation, and it's got the blues and reds and yellows and greens and so on and such like that. And this is a baby picture of the Big Bang explosion itself. It's important we have this image because when we're looking at this picture, we can see that the Big Bang explosion was not neat and tidy. It was rather non-homogeneous. It was rather gloppy, just a tiny bit gloppy. And that's important because those red areas you see are a place that has just a tiny little bit more gravity than the surrounding areas. And those tiny little imperfections are what led to the initial formations of galaxies and stars, and of course, life. If there were no stars to make heavy elements, there would be no planets, there'd be no people. And so you and me and everything alive around us and all the other living things in the universe, if there is stuff out there, are all due to imperfections billions of years ago. And so sometimes having a perfect universe is not what you want. You want a slightly imperfect universe, otherwise maybe things don't go so well. Well, what I'd like to do next is travel back to Earth because we've seen some pretty amazing things. And so let me turn our galaxies back on, all the known galaxies, just because it's so much fun to fly through data. There we go. All right, and let's fly back to Earth, everybody. home, everyone. Tiny little blue speck out here in the cosmos. Now, if any of you are feeling very small at this point, that's okay. But there's something important you should remember, that just because you are small out here in the cosmic stage does not mean you're insignificant, and that each of us has a role to play in the universe, and the tiniest act of kindness and preservation of this beautiful blue planet can be very significant for each other and our eventual exploration out into the cosmos. And it's important to see that we are a tribe of a very small place, and that we should maybe start thinking of each other as the same tribe instead of us versus them. It's all us, all humans preserving our beautiful spaceship Earth in this vast stage, the cosmos, and maybe we'll get out there if we start working together. Thank you, everyone.